Welcome to this introduction to amortized analysis. The idea is to give a simple introduction to the topic. The video will consist of a collection of examples, so you can also simply watch a couple of the examples and that will give you the idea of amortized analysis. So let's start with the first example, and that is a multi-pop stack. So this is a bit of a toy example, but in actual code you will have code that looks somewhat like this. So let me run through the code before I say more about the operations that we're using there. So the input here is an array A of length n, and we're using a stack, and it will be a multi-pop stack in the following way. So let's say this is the input A, and this is a stack which is initially empty, and now we have this for loop, and what this for loop does, it checks whether the current value in the array, so we loop over the values of the array, if the current value is smaller or equal to the size of the stack. The size of the stack is simply the elements currently in the stack. So we're comparing 5 and 0, so that won't happen. Now we push that element into the stack. And push for stack simply means we're inserting. This will continue, so we next have the 7. The 7 is not smaller or equal to 1, which is the current size. So we simply push. We push the 9. Now we have 2 is smaller or equal to the size, which is now 3. So and now we have the if case, and in the if case we have this concept of multipop. And multipop simply pops k times, or in this case ai times. And pop is for stack means that we're removing the element that was last added, and also we port that element. So in this case, that would mean, so we do multipop with AI. AI is 2, so that means we pop 2 elements. So we're going to pop the 9, and we're going to pop the 7. And then we insert the 2. And this algorithm doesn't have any purpose. It's just an illustration of this use of multipop. Now we have the 8. We simply push the 8, we push the 6. For the 3, 3 is smaller or equal to 4, so we pop 3 elements, push the 3. And this is a toy example, but the question simply is, what is the running time of this algorithm? Let's make this a quiz. Is it linear, is it n log n, or is it quadratic? The correct answer is linear. This may or may not have been obvious to you. It is not that obvious how to analyze it given this code. And that's what amortized analysis to some extent will be about. So let's try to analyze the code as it is. So first of all, we have to have some kind of stack implementation. Let's say we have the stack as a simply linked list. That means that all of the operations, push, pop, size, we can all get in constant time. Multipop we cannot get in constant time, because multipop simply does pop k times, or as often as, possibly only as often as there are elements. So that is O of, so let's say we can always pop all the elements that we want to pop. That would be O of k. So now let's plug that into our algorithm up there. So essentially everything is constant time except for the multipop. And the multipop, so we multipop AI, so we could say that's O of AI. As a direct estimate in terms of I, what we can say that we won't be popping more elements than I, because that's the maximum number that the array currently can have. So that's why I here give O of I, because that's a bound on the current size. So this is within a for loop. So we have this for loop with index I. So what we get naturally, if you just do the running time analysis as we kind of learned it, we get a sum over O of I. That's the arithmetic series. The arithmetic series, if we go to n here, evaluates to O of n squared. So that's the bound on the running time that we get in this way. But that's too pessimistic. We already said it should be linear. But how can we analyze this algorithm to get a linear running time? That's what amortized analysis is about. So what we do here is we're not looking at these operations individually. So we're not looking at an individual multipop, but we're going to look at the sequence of n operations. And we compute the worst case running time for that, and then the average, the amortized average running time for one operation. That's simply the worst case running time of that operation averaged over the whole sequence. We're going to see two methods for that, the aggregate analysis and the accounting method. So very often in the setting there's a third method that's discussed, the potential method. We won't do that because I wanted to keep things simple. And we're going to look at three examples: a multipop stack, which we already started with, a binary counter, and dynamic arrays, more specifically inserting into a dynamic array. So let's have a look at the aggregate analysis and then at the accounting method, both by the example of a multipop stack. So the aggregate analysis simply takes the worst case running time of a sequence of n operation, computes that, so computes the total running time, so that's why it's called aggregate. And then the amortized cost is, for one operation, is simply set to this total running time divided by n. If I have n operations, T of n divided by n. How does this look like for our example? In the algorithm that we had a mixed sequence of, so actually we had a mixed sequence of pushs and multipops. But let's say we have a mixed sequence of push, pops, and multipops. Furthermore, we were starting with an empty stack S. So that is our setting, and now we want to analyze the running time of the whole sequence. One way to do this is that we first bound the running time for all pushes. So we don't know how many of these operations are pushes, but we know, because we overall only have n operations, that there are at most n push operations. Each push operation takes constant time if we have stack efficiently implemented, like let's say with a linked list. So we have at most n push operations, each taking constant time. That gives us linear time for all the pushes in the sequence. Now for the pops as such, not for the multipops, for the pops as such we could do the same estimation, but we do a slightly different estimation here, and that is the following one. We say the number of pops is actually bounded by the number of pushes. Why is that the case? Because we can only pop an element if we previously inserted it, if we previously pushed it. But since we started with an empty array, so now that assumption comes in and is important, since we started with an empty array, only the elements that have been pushed by the sequence can also be popped. So the number of pops is smaller equal to the number of pushes is smaller equal n, and because every pop takes constant time, this gives me again a bound of O of n. But, and this is why we did this bound slightly different than for the pushes, these pops, so this analysis holds for all the pops, also the pops that happen within the multipop. Yeah, also multipop can only pop if the element previously was pushed, and any element that is pushed can only be popped once, because then it's gone. So we get O of n including all pops of the multipop, so including in particular all multipops. That means that the overall running time of a sequence of n such operations is linear, and then if we want to have the amortized cost per operation, that's T of n, the overall running time, divided by n, so that's O of n divided by n, that is constant, O of 1. So from this we can conclude that the average cost of an operation is constant. Stated differently, if I now have the loop that we previously had over I, then I can say that the whole sequence takes linear time. So this is the answer already to what the first quiz. We indeed get linear time, and this is a suitable analysis. We're now going to do an alternative analysis, and that is called the accounting method. It's slightly more complicated in the setup, but then it is a very conceptually very clear analysis, and also simpler, commonly simpler than the aggregate method, because we don't need to deal with quite as complicated sums typically. So what do we do? So here are some quantities that we define. DI is the data structure after the ith operation, and then we have the actual costs of the ith operation and the amortized cost of the ith operation. So the actual costs are the actual costs. The amortized cost is something that we assign. And we think of this as a payment or token, or as I say here, coins. Yeah? So you can think of assigning coins to an operation. So these amortized costs can be larger or smaller or equal to the actual cost. And depending on whether they're larger or smaller, this means that we're kind of actually saving coins or paying coins. So if the amortized costs are larger than the actual cost, that means that some of our coins we can keep, and those we save with our data structure. And then if at some point we have amortized costs that are smaller than the actual cost, so then the amortized cost cannot cover the actual cost. So at that point we should make sure that we have saved enough to actually pay for the difference. And the initial credit that we start off with is 0. So D0, the data structure at the beginning, has no credit. So the invariant that we want to maintain will be the following, namely that at all times the coins that we have, the saved coins, are larger or equal to 0, so no negative. In formulas this means, because saved coins means amortized cost minus actual cost, so the sum of amortized cost minus the sum of actual cost at any point in an algorithm should be non-negative. And our task will be to pick the amortized costs in such a way that this invariant can be maintained. So if we have this invariant, it immediately implies that we get a bound on the actual costs, namely the sum of the actual costs is bounded by the sum of the amortized costs. And those will have a sign that we can easily calculate with them, so that will give us a nice and simple sum, hopefully, and in particular then an upper bound on the actual costs. So the intuition here is that we're measuring the running time in terms of these coins. Or stated differently, time is money. Let's do this for the multi-pop stack. So the actual costs are the following. So push and pop in a stack costs O of 1 in terms of the running time or in terms of elementary operations. So we're going to say that actually costs 1 coin. So a push or a pop costs 1 coin. If we want to do a multi-pop, and let's say we can always do k, actually pop the k elements, so a multi-pop is always successful, then that costs us k coins, namely for each pop operation 1. The invariant that we will want to maintain, and that will guarantee us that we will have saved enough, is the following. With every element in the stack, we're going to save a coin. So if this is my current stack, with 3 elements, I will have already saved 3 coins. To make this work, we will assign the following amortized costs. So for every push, we assign 2 coins. 1 coin to pay for the push, and 1 coin to save. So if we now, for instance, push 8, what we'll do is the push as such costs 1 coin, so that's this coin, and the other coin we're saving with the 8. Now to pop, we again need to have coins, but for pop we already have saved the coin. So if I now want to pop, let's say the 8, then I can use a coin that is already lying there. So that's why the cost that I assign, the amortized cost that I assign to a pop, is simply 0. Yeah, so if I want to pop here, I can simply use the coin that is there. Small quiz: how many coins do I need to assign to multipop? 0, 1, or k? So the correct answer here is 0, just like the pop, because the same argument holds. Even for a multipop, we can simply pay with the coins that we already saved. So for instance, if I do multipop with k being 2 here, So meaning I'm popping two elements. Those two elements have coins saved with them, so those can be used to pay for the multipop. In this way, we always have that this invariant that I formulated up here, that for every element in the stack there's a coin, that invariant is maintained. So in particular, the invariant that the number of saved coins is always non-negative is maintained. With this we get the following results. The running time of a sequence of n push-pop or multi-pop operations starting with an empty stack is linear, and the amortized cost per operation, because that's how we were assigning it, is constant. So also for the zero, that we simply call constant. The invariant that the number of saved coins is non-negative, that simply follows from the invariant that we phrased up there, that the number of coins that we have corresponds to the number of elements in the stack, and because there's always a non-negative number of stack elements, at least zero, we always have at least 0 coins. This together with the bound on the amortized cost, so any operation costs at most 2, namely the push costs 2, everything else costs even less, gives us that the actual costs, so here we have the actual costs, we can bound them by the amortized cost, or more specifically the sum of actual costs by the sum of amortized cost. For the amortized cost we can upper bound them by 2, and this gives us a bound of 2n for our actual cost. So this was an alternative analysis for analyzing multi-pop stacks. So this again tells us that this algorithm that we saw at the very beginning runs in linear time. So what have we seen so far? What we want to do is amortized analysis. So that means that we have a sequence of operations and we take the amortized average over that sequence. We are looking at worst case. And the methods that we've seen were the aggregate analysis, and there the idea was really to simply compute this T of n, the worst case running time of the whole sequence, and then as amortized cost take T of n divided by n. For the accounting method, we had these coins that can pay for later operations. We had this invariant that we wanted to maintain that says something about coins that we've saved. And then in the accounting, we have to set the amortized cost in a suitable way, so assign coins to operations in such a way that we can maintain whatever invariant we formulated. And the example that we saw was the multi-pop stack. The next example will be a binary counter. So let's look at a k-bit binary counter. So here we have 6 bits. So we have, and we can represent that by an array. And the jth, aj is simply the jth least significant bit. So a0 is the least significant bit, simply. Meaning that, for instance, if I want to represent a 0, okay, that's simply the all zeros. If I want to represent the 1, that is simply a 1 at a0. And now we want to increment our binary counter, and increment it again and again and so on, and see how expensive that sequence of operations is. So how expensive is one step in this counter? It's as expensive as the number of bits that I need to flip. So here from 0 to 1, I'm flipping the a0 bit, so that has a cost of 1. Then for if I go from 1 to 2, I need to flip a0 and I need to flip a1. So the 1 goes to becomes a 0, the 0 a 1. So that has a cost of 2. Then from 1 to 2, no, from 1 to 2 we just had. From 2 to 3, from 2 to 3 we only have to switch a0, because 3 is 2 times 1 plus 1 times 1, 3. So there the cost of updating our counter is 1. And in this way, so the blue here indicates how expensive each of the increments is. But what we're looking at here is the cost of flipping, and that is a number of bits flipped. So if I have a k-bit binary if I have a k bit binary counter, the numbers of bits that I can flip in one step is at most O of k. That gives us a worst case running time, or an upper bound on the worst case running time, if I do a sequence of n increments of O of k times n. But this is too pessimistic. So again, here what we want to show is that this does not depend on k, this only depends on n, and in particular we simply get a linear running time. How do we prove this? So let's start with the aggregate analysis. So here we simply try to, in whatever way works, compute t of n, so the running time, the worst case running time of a sequence of n increments starting at 0. And the way we can analyze this is by looking at each of the bits and asking how often is that flipped. So how often is ai flipped? Let's start with a0. A0 is flipped, okay, you already see here it's actually flipped n times. It won't be flipped more than n times because we only do n increments. So we have here simply an n times. How often is a1 flipped? So a1 is actually flipped every second time. What does that mean? It means that we have n half flips of a1. We have n quarter flips of a2, and so on. So the ith bit is actually flipped n divided by 2 to the I times. So the total cost is the sum over all the bits. So I goes from 0 to k minus 1. So here in the example of k is 6, it went from 0 to 5. And then n divided by 2 to the I. So we're starting with n, and then we get, when I is 1, n half, when I is 2, n quarter, and so on. This is a sum that we should recognize. So in particular, or at least if we can rewrite it slightly. So let's have as an upper bound. So here we're rounding down, so we can simply write it as a sum that goes where we take n divided by 2 to the I, because if we don't round down, it just makes it larger. Then we can take the n outside of the sum, because that doesn't depend on I. So let's do that. Let's take the n outside. Now we have the sum, 1 divided by 2 to the I. It goes up to k minus 1, but this is the geometric series. And even, so again, if we just take an upper bound, even if we go to infinity, this is simply bounded by a constant, namely 2. So we have 1 plus 1 half, plus 1 quarter, plus 1 eighth, and so on. It kind of converges to 2. And in particular, it stays smaller than 2. So we get, as upper bound, 2n. So overall, at most, 2n flips happen. So let's formulate this as a result. The worst case running time, t of n of a sequence of n increments, is linear. So the amortized running time of one increment is t of n divided by n, constant. This was the aggregate analysis, and here we were already working with not so nice sums, you could say. I mean, it was not that complicated, but we can do it simpler, namely using the accounting method. So let's do the same analysis with the accounting method, and that will actually be quite elegant. So what do we need to do? We need to decide on, okay, we do have the actual cost per operation, so we pay 1 coin per bit that we're flipping. Now we have to think about which invariant do we want to maintain, and how do we set the amortized cost. So how do we do all of the accounting? So let's look at an example. Let's look at a specific number, 23, for instance. 23, if k is 6, looks like this. So we have 1 plus 2 plus 4 plus 16. If this is a number that I currently have, which of the following invariants is suitable? Where should I have coins lying in my data structure? And let's simply keep this visual. So is it A, B, C, or D? So the correct answer here is B. So we will want to have 1 coin per value that is 1, per AI that is 1. So why is that the case? The intuition here is that it can happen that we will need to flip many ones. Yeah, so if I now, for instance, add 1, if I go to 24, I will need to flip all of these. So all of these will become 0. This one will become a 1. So for each of these ones, I will need to have a coin that pays for it. Now you could say, oh, this is enough, but of course, sooner or later, I will also need that one. Namely at the point where that is flipped. So it's good to have already saved something there. Okay, so how do we set our cost then? Every time we increment, we pay 2 coins. Or we assign to each increment 2 coins, because this allows us to pay for the following. So with every increment, there is a 0 that goes from 0 to 1. So here in our example, this 0 becomes a 1. And there's exactly 1, because as soon as we, so if we have 1s here on the right hand side, so all of those will be flipped until we find a 0, and that becomes a 1, and then that ends up flipping. So there's a 1 0 that is flipped. And to pay for that flip, we need a coin. So we have 1 coin that pays for flipping this 0 to 1. And what is the purpose of the other coin? The other coin we place at that 1. Because there's a new 1, it needs a coin. Yeah, so this looks like that. 1 coin for paying. Yeah. 1 coin for saving. Now we have a 1 with every coin again. So what does that mean for us? It means that anytime I flip a 1 to a 0, I do actually have a coin that can pay for that, because we saved coins. And then after flipping, that 1 is a 0, so at that point we don't need a coin anymore there. In the 23 example, all of these become 0, and we can pay with the corresponding coins that were lying there. This again allows us to analyze the worst case running time of the increments in a binary counter using the amortized cost that we now assigned, and the worst case running time T of n of a sequence of n operations. We can now again conclude that it's linear, and the amortized cost per operation, simply because we defined it as something that is constant. The proof of this statement is as follows, and this is now again exactly the same as for the multiprop stack. So we have the invariant, and the invariant in particular tells us that the number of coins saved is always non-negative. So we're saving 1 coin. We have 1 coin per 1. We have at least 0 ones, so we have at least 0 coins. Per operation, the amortized costs are bounded by 2. Actually, we have a 2 for each operation. And then the actual costs, which we have here, are bounded by the amortized costs. We plug in the 2, we get a bound of 2n. And this was the analysis of a binary counter, once using the aggregate analysis and once using the accounting method. So the last example that I want to show you are dynamic arrays, specifically inserting into a dynamic array, and in particular using the accounting method. So I'm not doing the aggregate method. So I have a video about dynamic arrays, so that's the first part of the elementary data structures. There is the dynamic arrays with the aggregate method, but here we simply do accounting method. And now that we have all of this machinery, it's the more elegant analysis, I would say, but you can judge. So once more, what is the setting here? We want to have a dynamic arrays. We want to be able to insert in such a dynamic array. We are going to implement it using a static array. So a static array is very useful. It's very fast. we have random access, it's compact in terms of memory, but the problem is it's fixed size. And that is a problem if we want to use it for other data structures. For instance, if we implement priority queues, so if we want to have heaps we want to have variable size. Hash tables, we also often enough want to have variable size, so that if we inserted too many elements, so if it becomes too full, we again have enough space. We can achieve this if we would have a dynamic array. So an array with an append operation where I can insert an extra element at the end, going beyond what would have been the fixed size. And this is something that you have in programming languages and use very frequently. So in Java, it's an array list, C++ vector, Python list. So in Python, you don't even normally use an array, a fixed size array at all. You always use a dynamic array. And those are all implemented using a static array in the background with the following idea. If this is my setting, so I have an array which contains 3 elements, but there's only space, and there's space for 1 more, but we want to insert 2 more. Then we simply increase the size, and we increase the size by some constant factor. And for the purpose of this video and for the purpose of getting simple analysis, let's assume that factor is always 2. Let's say we always double in size, but of course we cannot simply double the size of the given array because that array had fixed size. So what we do instead is we make a new array of twice the size, and then we need to copy all of the elements into that new array. Meaning that the cost per operation is linear anytime I need to do this. So it's linear if n is, so if we do this doubling and we start with size 1, it's linear whenever we go have a power of 2 and then add 1. But only then it's linear, otherwise for all other appends it's constant time. So what is the worst case running time of n operations? If one append takes worst case linear time and I do n appends, then the obvious upper bound that we get is quadratic, so n times n. But as we now know by now at this point in this video, this is of course too pessimistic. So let's get a tighter bound, and for that let's use the accounting method. Again, we start with the actual cost per operation, and we assign 1 coin for 1 insert, so for 1 append operation. Then we either simply append 1, or we need to copy n elements to a new array of size 2n. So let's say that this copying process, that cost me n coins. I mean, it costs O of n. So let's simply call this n coins to copy n elements. So those are the 2 operations that are happening within an append. The invariant that we're going to maintain is the following. Every element in the right half of my array is going to save 2 coins. So here I have an array of size 8. So right half, those are the last 4 elements, or the last 4 positions. Right now we only have 2 elements, and each of those has 2 coins. If this is the invariant that we want to maintain, how high do we need to, so what amortized costs do we need to assign for this to work? Should they be 1, 2, 3, or n half? Correct answer here is 3. So why 3? Because every time I append, so let's say I append a new element here, then I want to place 2 coins here, and the append itself also costs 1. So I assign a cost of 3 to append because 1 coin pays for the append, 2 coins are saved. So let's do that by example. We insert the 1, we're saving 2 coins while paying 1. Now let's add another element, a 3, we're saving 2 coins while paying 1. Now at this point, let's say I would be inserting another element. At this point, I would have to pay this cost. And so in the next step, I would have to pay n coins. In this case, n is 8. Yeah, luckily, we have n coins sitting here. So if the array is full, it means that we have n half elements in the right half of the array. Each has 2 coins, and half times 2 gives me n. I have n coins. Those n coins can pay for the actual costs here. And then after doing this, so after doubling, we would be in a situation where, so this was 8, so we have 8 more here. Now at this point there are no coins left, but that is not a problem because the right half now is just this part here, and as long as that's empty, I don't have to have coins. Only if I insert, I will be inserting an element now here, and that element will come with 2 new coins anyway. So we're fine. So what do we see here? We see that the worst case running time of a sequence of n appends is O of n. That means the amortized running time of one append is constant. And how do we get that? It's the same analysis as always. The invariant here tells me that my savings are always non-negative. With that, we get as an upper bound on the actual cost or sum of actual cost, the sum of amortized costs. The amortized costs always are 3, so we get 3n as an upper bound, and that is it. And the amortized cost of an operation, that is simply a constant. So much about inserting into dynamic arrays. So there's also an amortized analysis of if we want to delete in dynamic arrays and we want to again resize, so shrink the arrays. So that's also very interesting to keep things somewhat not too long. I'm leaving that out, but that is something for you to figure out if you want to. So there's a bit of, you have to be a bit careful that you don't resize too early. Imagine you always immediately, so let's say I increased my size here, and now because I have a new element here, then I should not do the mistake of when deleting that element immediately shrinking my array. And from this you'll immediately see why you shouldn't be doing that, because at that point you haven't saved any coins for paying. So in this example, the point where we want to resize is at the point where we actually also deleted these elements, because at that point we can have saved enough coins, but that is an amortized analysis of itself. So this is what we've seen. We did an amortized, we were doing amortized analysis, so that means we were looking at sequences of n operations and asking about the average or the amortized cost of one operation, and that meant taking the average over the worst case operations of the whole sequence. We've seen 2 methods, the aggregate analysis and the accounting method, and 3 examples, multipop stack, binary counter, and dynamic arrays. And that's all for today. See ya.